This is the 31st in a series of videos that I'm making to support a course in elementary number theory. And we're finishing this course up with a study of integer partitions, really just dipping our toes into the subject of integer partitions and the mathematics of Ramanujan. And he approached integer partitions using q-series. And so this video today is really just about working with q-series and different q-series identities. It probably won't be immediately clear how this is applicable to number theory, but when we pick up with the next video, it'll become more clear. Okay, so let's look at a couple of definitions first. And so this is the definition of the Pockhammer symbol, AQN, which is sometimes just abbreviated AN. And that's going to be the product as m goes from 0 to n minus 1 of 1 minus a times q to the m. So that expands out as 1 minus a times 1 minus a q times 1 minus a times q squared. And that finishes with 1 minus a times q to the m to the n minus 1. So that's a finite product. But there's an infinite version of this object. And so that's aq infinity or just a infinity. And that's the product as m goes from 0 up to infinity of the same thing. So that's essentially what we have up here, just an infinite product instead of a finite product. That's a little bit messy, but that ends at n minus 1. So it's a product of n terms. Okay, so our first theorem that we'll prove today is sometimes called the q-binomial theorem. And that says for q and z, whose modulus is less than 1, we have the following equality of a sum and a product. So notice this right-hand side is a quotient of things like this. So it's just written purely as a product. We could even write this out if we want to as the product as m goes from 0 up to infinity of 1 minus a times z times q to the m in the numerator over 1 minus z times q to the m in the denominator. And then we would expand each of those things in the denominator using geometric series, and it would sum up to this thing over here. So these sum product identities are really important in the study of partitions. And actually one of the most famous partition identities, the Rogers-Ramanujan identities, is one of these sum product identities. Okay, so let's get to the proof. So we're going to start with this right-hand side, and we'll give this a new name. So let's maybe set a of z equal to this az infinity over z infinity. And then let's assume that it can be expanded as a sum in the following way. So this will be the sum as n goes from 0 up to infinity of a sub n z to the n. So it's like a power series in z. So notice in order to finish this off, what we'll want to show, that an is in fact equal to this guy right here. So it's this Pockhammer symbol an and then qn. That's what we want to end up with. If we can get to that yellow box, then we've proven this theorem. And so what we're going to start by doing is looking for a recursion among these coefficients. And we can do that by multiplying this a of z, which is this product form of our would-be identity, by a couple of different things and noticing that we've got some sort of relationship here. So let's take 1 minus little az times a evaluated at qz. Okay, so let's see what we've got. This is going to be 1 minus az, and then we'll rewrite this a evaluated at qz using this infinite product. So that's going to be the product as m goes from 0 up to infinity of 1 minus, now notice z is being replaced with qz. So maybe we would write this as az q to the m plus 1 over 1 minus, again, z is being replaced with qz. So we have z times q to the m plus 1 like that. But now let's write out some terms so we have a feel for what this looks like. So this looks like 1 minus AZ. That's the first term in the numerator. I'll just write this as one of the terms in the numerator. And then the second term in the numerator, which comes from the first term of this product, is 1 minus AZQ. So notice that's the m equals 0 term here because we have q to the m plus 1. And then next we have 1 minus AZ times q squared, and then that just goes up infinitely. Now let's see what the denominator looks like. So the denominator is going to look like 1 minus z times q, and then 1 minus z times q squared, and then that's going to infinitely go up. Okay, then next we can see that this numerator is actually one of the products that's defined over here. This numerator is in fact AZ infinity, which is actually good news. And then this denominator is almost one of our products over here. We can turn it into one of our products over here if we multiply it by 1 minus z, but that means we need to multiply the numerator by 1 minus z as well. So what does that turn the denominator into? Well, that turns the denominator into z infinity. Okay, cool. So let's see where that leaves us. That means we have 1 minus z times az infinity over z infinity. But notice this az infinity over z infinity is exactly our function a of z. So this is equal to 1 minus z a of z. So let's really carefully look at the extreme left hand and right hand side that we have built here. And that's a nice, fairly simple expression for our function a. So let's maybe consolidate that, and then we can use this nice equation that we've built to get a recursion on our coefficients a of n. After defining our function capital A of z, we just derived the following nice equation involving a of z. Now we want to put that into our expansion and see if we can get any information about those coefficients a of n. So we've got 1 minus little az times the sum as n goes from 0 up to infinity of a of n times q to the n z to the n. So that is this AQZ expanded as our power series. And then over here on the right-hand side, we have 1 minus z, and then our sum as n goes from 0 up to infinity of anz to the n. Now we're going to distribute this sum through both of these parts on both sides of the equation. So that's going to give me my sum as n goes from 0 up to infinity of an q to the n z to the n minus my sum as n goes from 0 to infinity of little a times a sub n of q times q to the n z to the n plus 1. So that's how this builds up when we distribute it through. And then over here on the right-hand side, obviously multiplying by 1 is not going to do anything, so I can just bring this down. And then multiplying by z will bump that exponent up by 1. So I've got my sum as n goes from 0 up to infinity of anz to the n plus 1. Okay, nice. So where do we go from here? I think our best bet is to notice that this term right here, maybe I'll underline it or I'll overline it in pink, and this term right here are the only two sums that have a constant term. Notice this sum starts at z to the first power, so does this sum. And the constant term in both of these sums is a0. So we might as well subtract a0 from both sides. So let's write that here. Both sides, we will subtract a0. But what effect does that have on these two sums? That means these two sums can now start at n equals 1 instead of n equals 0. But what's the use of that? Well, the use of that is now we can re-index these two sums so that we have the same index and the same exponent of z. So now let's replace n with n minus 1. And now notice when n minus 1 equals 0, that means n equals 1. So that's going to bump this from starting at 0 to starting at 1. And now we'll have an n minus 1 here, an n minus 1 here, and then an n minus 1 plus 1, or just an n there. So that's just from re-indexing this sum. And then we can do the same thing over here. We'll replace n with n minus 1. That's going to mean this will start at 1. This will be now n minus 1, and this will be z to the n. Okay, nice. But now we can push these two sums together and then extract coefficients, because the coefficients of all powers of z must be equal on both sides of this equation. So instead of pushing the sums together and extracting coefficients, let's just extract coefficients. So extracting the coefficient of z to the n on the left-hand side of the equation will give us a sub n q to the n minus little a times a to the n minus 1, or a sub n minus 1 q to the n minus 1. Then extracting the coefficient of z to the n on the right-hand side of the equation will give us a sub n minus a sub n minus 1. So now we've got this nice recursion involving q's and our a sub n and our a sub n minus 1. So now let's bring this red dot back up to the green dot, and then we'll keep going. We're actually almost done with this proof. On the last board, we built the following nice recursion for our coefficients a sub n. Maybe I should have pointed this out earlier, but these coefficients a sub n in our expansion of our function z will depend on q. So sometimes these are written as a sub n of q. You don't strictly need to do that because that's kind of assumed here, given that this object here depends on q. Okay, where can we go from here? Well, we're going to move everything with an a n minus 1 to one side of the equation and everything with an a n to the other side of the equation. So what I'll do is take this guy and then move it to the left-hand side of the equation. And then I'll take this guy and move it to the right-hand side of the equation. So that's going to leave me with a n minus 1 minus a n minus 1 times q to the n minus 1 equals a n minus a n q to the n, like that. Now let's factor some stuff out as we can. So here we'll have a n minus 1. Then we'll have 1 minus a times q to the n minus 1. Okay? And then over here we'll have a sub n and then 1 minus q to the n. Let's see, where can we go from here? Now we can write a sub n in terms of a sub n minus 1, which is super nice. So notice that a sub n can now be written as 1 minus a times q to the n minus 1 over 1 minus a q to the n, a sub n minus 1. But now we can just apply this over and over and over again until we get down to a0. So let's do maybe a couple of steps of that explicitly, and then I think the pattern follows pretty easily. Okay, so after one step, we'll have 1 minus a q to the n minus 1, 1 minus a q n minus 2 in the numerator, over 1 minus q n 1 minus q to the n minus 1 in the denominator, and then a to the n minus 2. But now notice what we're going to have is this falling product in the numerator and the denominator. Each time we pick up a term that looks almost exactly the same with one lower exponent of q. That's happening upstairs and downstairs. But that's going to extend all the way until we have a q to the 0 power here. So in other words, we'll have 1 minus a. And we'll have a q to the 1 power over here. In other words, we'll have a 1 minus q. But that means that we'll have this product a sub n, so 1 minus q, all the way up to 1 minus a times q to the n minus 1 in the numerator. And in the denominator, we'll have the same thing with a replaced with q. So just to like really spell that out, we will have the Pockhammer symbol an in the numerator and qn in the denominator times a0. So let's see what we've got. We've got a sub n is equal to this in terms of a0. But now we just have to figure out what a0 is. So a0 is the constant term of this sum. But we can figure that out just by looking at this expansion. And notice that the constant term of this expansion, when everything is expanded as a geometric series, will just be the number 1. So that means we can take this a0 here and just replace it with the number 1, meaning we have built this formula in the yellow box, which is what we wanted in order to prove this identity. Okay, so let's maybe get rid of this proof and we'll look at a corollary. Okay, so let's look at a really quick corollary of this big theorem that we just proved. And that is the sum as n goes from 0 to infinity of z to the n over the Pockhammer symbol qn is just 1 over z infinity. So let's see how this proof might go. So it's actually quite simple. What we'll do is take this big theorem that we just proved and set a equal to 0. So let's just get a feel for why that works. So notice this symbol an, by our definition over here, is 1 minus a times 1 minus a q all the way up to 1 minus a times q to the n minus 1. But pretty clearly, if we set a equal to 0, this just collapses to the number 1. But that collapses this left-hand side to our left-hand side here. Let's see what happens to this az infinity. So our az infinity is 1 minus az times 1 minus azq, but that's an infinite product. But the same kind of thing is happening. Notice if we set a equal to 0, that collapses this thing to 1 as well. Okay, nice. So let's maybe get rid of this, and we're going to prove another theorem that is somewhat similar to this, but I think it's useful to look at that proof as well, just for practice dealing with these kind of things. Okay, so for the next theorem, which is sometimes presented as a corollary of the last theorem, but like I said, we're going to prove it from scratch for practice. So that's the sum as n goes from 0 up to infinity of minus z to the n, q to the n times n minus 1 over 2 over qn is equal to zn. Now this exponent here of q, this n times n minus 1 over 2, may seem like it came out of nowhere, but we'll see that it arises quite naturally in our proof. Okay, great. So now let's get going here and we'll do the same kind of thing that we did before. We will assume some expansion of the product side and then find a recursion on the coefficients of that expansion. So let's maybe go ahead and set our product side z infinity equal to, I'll call it az again, just like we did in the last proof. And then this will be the sum as n goes from 0 up to infinity of an, and then instead of doing z to the n, being inspired by what we see in the theorem, I'm going to do minus z to the n, so it's an alternating sum. So let's see, what does that mean we want to end up with for our a sub n? So just to reiterate, we want to show that our a sub n in this case is equal to q to the n times n minus 1 over 2 over the Pockhammer symbol qn, like that. Okay, so let's get going on this. And like I said, we're going to do the same kind of strategy that we did before. So let's start just by looking at az, but expand it out as a product here. So that is 1 minus z times 1 minus z times q times 1 minus z times q squared, but an infinite product. This is just to get an idea for how we can put these things together. Next, let's look at A evaluated at q times z. Being inspired by what we did in the last proof, this is actually a pretty common method to evaluate this kind of thing at qz. So that's going to give us 1 minus qz, 1 minus zq squared, 1 minus zq cubed, and so on and so forth. So that's a little annoying. Let's rewrite that as zq. But what relationship can we see between these? Well, let's notice that this guy right here, this a of z, is exactly this guy right here, this a of qz, times 1 minus z. And we can see that because of this kind of shifting behavior that we get when evaluating at q times z. So let's write that observation down here. So we have a of z is equal to 1 minus z times a of zq. Now we're going to play the same game that we did before. We're going to expand each of these. So this is going to be the sum as n goes from 0 up to infinity of a sub n minus z to the n equals 1 minus z, and then my sum as n goes from 0 up to infinity of a sub n and then minus z to the n times q to the n. I'll pull those apart just kind of as needed. Next, I'll multiply this through, and let's see, that's going to give me this sum as n goes from 0 up to infinity of a n q to the n minus z to the n. That's from this one term. And then minus my sum as n goes from 0 up to infinity of a n minus z to the n times z times q to the n, like that. So I need to be a little bit careful with my z because it's wrapped up with this minus 1. And in fact, we could be a little bit more explicit if we took this apart into two parts. So we could write this as minus 1 to the n, z to the n plus 1 at this point. Great. And then that means over here, we could do something similar. Write this as minus 1 to the n, z to the n. Okay, so let's take that expression and bring it up to the next board. Okay, on the last board, we manipulated our expansion for our function a of z, which was this product, down to the following relationship between these coefficients. Now we just have to do a little bit of work on these series to extract that relationship between the coefficients. So we'll start by noticing that the only occurrence of a0 just by itself with no power of z or q happens here and here. That's because if we have n equals 0 here, we've got z to the first power. So what we'll do, just like we did on the last board, we'll subtract a0 from both sides. So that's the first term from this series, or maybe we should say the 0th term from this series. And it's also the 0th term from this series. So that means we can take these zeros and replace them with 1 because, again, we've subtracted the same thing from both sides of this equation. Now we're going to play a game over here. We're going to re-index. So we'll replace n with n minus 1. So if n minus 1 is 0, that means n is 1. So that means we'll start here at 1. But that means all of these are going to change. This will change to n minus 1. So will this. So will this. And then this will change from n plus 1 just to n, like that. Okay, nice. Now we can extract the exponent of z to the n from both sides of this equation. So notice the exponent of z to the n from this side of the equation is just minus 1 to the n times a sub n. the exponent of z to the n from this component right here is minus 1 to the n, q to the n, a sub n. Okay, nice. Finally, the coefficient of z to the n from this last sum is equal to minus 1 to the n minus 1, q to the n minus 1, a n minus 1. Okay, nice. Now, where can we go from here? Well, notice I've got these minus 1 to the n's all over the place. Maybe we'd like to get rid of those. And we can get rid of those easily by multiplying this entire equation by minus 1 to the n. So let's see what effect that will have. That will turn this minus 1 to the n just into 1, so we can scrub it out. Same thing here, because we'll have minus 1 to the 2n. That'll change this to a minus 1, but that minus 1 can be used to change this minus to a plus. So we've got something like that. Now we can move everything with an an to the one side of the equation and everything else to the other side of the equation. So that gives us an minus q to the n an from moving this over equals q to the n minus 1 an minus 1. But we can factor an an out and then divide by what's left, and we'll see that we have q to the n minus 1 over 1 minus q to the n times an minus 1. We can repeat this over and over and over until we hit a0. So that's going to give us q to the n minus 1 over 1 minus q to the n times q to the n minus 2 over 1 minus q to the n minus 1 times an minus 2. And then keep going. So let's just jump to the last bit. So that's going to give us q to the n minus 1 plus n minus 2 plus all the way down to 2 plus 1 from multiplying those numerators together over 1 minus q to the n times 1 minus q to the n minus 1 all the way down just to 1 minus q. But that's exactly this symbol right here with a replaced with q. So we have qn. Okay. Well, let's look at what our an is at this point. It's this versus our goal, which is up there in orange. So they're almost exactly the same. Notice the denominators are the same, but the numerators are not quite the same. But if you look a little bit closer, you see that the numerators are the same, because here we have a triangular number. We have the sum, 1 plus 2 plus 3, all the way up to n minus 1. But that has a well-known closed form of n times n minus 1 over 2. So that will fuse this an into the right format. I guess I should say that I left something off. I left off an a0, but from an argument similar to what we had in the last proof, this is also equal to 1. In the next video, we'll expand on these types of ideas to come up with some nice partition identities. And that's a good place to stop.